Hello guys, welcome back to another video. In this video I want to convince you that this circle here is indeed a function. And I know what you're thinking. Well, a function takes only a single value of x and outputs a single value of y. For example, we can take this function here, that's a function because for a single value of x, it gives us only a value of y. Instead, this function here, for example, for this value of x, gives us two values of y, this value here and this value here. So this is not a function. We cannot express y as a function of x, right? Because what is the equation of a circle? The equation of a circle is x squared plus y squared equals to the radius of the circle squared. And if we try to isolate the variable y, we get y squared equals to r squared minus x squared. We can take the square root on both sides, and we need to put a plus or minus. So plus or minus the square root of r squared minus x squared. And as you can see, if we give a particular input x, we get two values, the plus of this quantity here and the minus of this quantity here. So we get 2 points. So this is not a function. It is described by two functions. We can take only the positive part and we get this arc of the circumference, or we can get the minus part and the minus function and we get this part. But we cannot describe them together. But there's a way to do that, because this circle can be represented by a function. And we shouldn't consider the normal functions, the simple functions, let's say from, so they take only an input and they give us an output, just a single number, and the output is another single number. In this video, we're going to introduce another type of functions. Functions from R, that is real numbers, so it could be a subset of real numbers, to R squared. And what does it mean? These strange symbols are weird, aren't they? It means it takes a number as an input and it outputs two numbers, or a vector. I think it's better to call it a vector. Obviously, a vector is represented at least in 2 dimensions as two numbers, because you have to give an x coordinate and a y coordinate. But this is also a function, and we're going to describe this circle as a function. So don't be scared of what I've written so far, because it's straightforward. Now, this is the equation of a circle, but how can we describe it as a function? So we need to introduce a parameter to describe our curve, and we're going to talk about what a vector valued function is. So let's take a point on this circumference here, let's take this point for example. It is described by an x coordinate and it is described by a y coordinate. Now we can draw this perpendicular line here and this perpendicular line here. So we can describe the point by a distance from the origin, that is the radius of our circle, and by another parameter, this angle here. And we choose it to be the angle between the x-axis and the radius, just as a convention. Now we know by trigonometry that the x-coordinate is simply r times the cosine of the angle theta, whereas the other coordinate, the y-coordinate, is r times the sine of theta. And now we can represent our function that we call r with an arrow on top to express that this is a function that takes an input, a single number, and it outputs two numbers, or a vector. And I'm going to explain you what this means. So we can write it in the following way. So we have x equals r cosine theta and y equals r sine theta, expressing its components, or in a more concise way using vector notation as r cosine theta and r sine theta, where the first row means the x component and the second row the y component. But I think there's a better way to describe it. And because there's not just a way to represent this function, because now we're using polar coordinates. They're called polar coordinates because we give an angle and a distance from the origin, and we can find every point in that plane using these two coordinates. So not using x and y, but using theta and r, we can find x and y. So what can we do? This is in the x direction and this is in the y direction. So what is a vector? It's just an arrow. It can be seen as an arrow pointing in space. For example, this arrow is our vector r that is pointing towards x and y, where x is r cosine theta and y is r sine theta. Or just a point in space, but sometimes it's more convenient to think of it as an arrow. Now, how can we describe this vector? Well, we can write it in the following way. We write the x component r cosine theta times another vector I plus r sine theta times another vector j. What does this I and j mean? Well, they're two unit vectors. I've drawn the at over I and j to express that they're unit vectors, so their length equals to 1. This is why it's sometimes more useful to think of them as arrows. And we can draw the vector, unit vector, on the x-axis pointing towards infinity, and on the x-axis, and the j at vector in the y direction. And we can express the vector as r as a sum of these two vectors, because what we're doing here is, for example, let's take the vector I. We scale it by r cosine theta, so we multiply it by r cosine theta and we get this yellow vector here. We do the same for j. We scale it by the quantity r sine theta, just a scalar multiple. Let me draw it in green so you can see it better. And this is our scale vector j. If we add the two just using the normal Pythagorean way we do that, we get the vector r. And as you can see, this is very important, because now r is just constant, just a number, because we looking at a circumference where the radius is constant. And if we give just one number as an input, theta, for example, theta equals pi over 2, then we know the coordinates of r. And for example, if theta is pi over 2, we get this vector pointing along the y-axis. If we say theta equals pi, we get this vector. If theta equals 3 over 2 pi, we get this vector, and so on. So as you can see, we can represent the circle as a function. Given one parameter theta, we get a new object called a vector that is made of two parameters, actually, because we can see it here, but it's a single object. And thanks to these new functions, we can describe curves in this example using the so-called vector valued functions, where we use a parameter to describe the curve, or even other stuff like planes in space and so on. But this is called a parameterized curve. This means that thanks to a parameter, we can get a curve. R is basically the curve itself, a point of the curve given a specific angle theta, and we can describe it as a function of x and y, or we can describe r as a function of r and theta, and in this case r is constant. So the vector doesn't depend on what coordinates you're choosing, but it is something even more fundamental from this point of view. And now we can see another thing. If we want to get back to this equation here, the equation of a circle, what can we do is the following. So let's take this equation because I think it's simpler to do it from here. We square both equations, so x squared equals to r squared cosine squared theta. We square the second equation, so y squared equals to r squared sine squared of theta. We add the two equations like we always do with multiple equations, system of equations. So x squared plus y squared equals to r squared cosine squared plus r squared sine squared. We can just take r squared out of the brackets, and we get r squared that multiplies sine squared of theta plus cosine squared of theta. But we know that this quantity inside the brackets is just 1, so we get x squared plus y squared equals r squared. So what we've seen today is that a parameter, the circle, can be described, and even more curves, even in 3D space, introducing another coordinate, the z coordinate, can be described by function. It's not true that this cannot be represented by a function. It cannot be represented by a function that takes an input and outputs another number, but it can be seen as a function that takes one number and gives us another object called a vector that is made of two components. So this is what I wanted to tell you today. So the next time when someone tells you that this is not a function, try to explain in that this is indeed a function. It's a new kind of function, a generalization of functions, but this turns out to be useful even in physics when we describe, for example, trajectories or other things like this. And it's also cool how you can differentiate these functions the same way, or kind of the same way you do it with normal functions. And we'll see that in another video. If you enjoyed this video, please subscribe to my channel, leave a like, a comment below, and as always, until next time, bye.